Hello, I'm Nikias Klohr, Head of R&D here at Result, and today I want to do a tech deep dive with you, talking about the battery life of our transponders. So, to start with, if you look at the basics, if you look at the capacity of our battery, we have a 225 milliamps milliamp hour battery, and we test every single transponder in production for a current consumption of 4 microamps or below. So whenever a transponder draws more than 4 microamps, it would be sorted out in production. Typically transponders use a little bit less than that, but this is a good worst case scenario calculation basic. So if you do the math on that, you end up with about 6.4 years, let's write that, years of battery life. And this is without deep sleep or anything. This is just the standard battery life of a transponder laying around in standby. So on top of that, you can add another 40% by putting the transponder into deep sleep. Obviously, you don't want to do that at all times, because then you would never use the transponder. But let's say you do it for 1 month, you would gain half a month of overall battery life, roughly. That's how you can calculate if deep sleep is worth it for you or not. Another rough estimation is that 1 day of tracking is worth around 1 month of standby. So if you consider using tracking, always keep this in mind, that for every full day of 24 hours you use the tracking feature enabled, you lose 1 month of overall battery life for the transponder. So, having covered the basics, you understand where we're coming from. If you see the 6.4 years that we calculate with the battery capacity and the current consumption of the transponder, obviously we are giving ourselves some headroom in our guarantee, and this is for generating passings. Every time the transponder generates a passing, it draws a little bit more. It is not absolutely repeatable, because it depends how quickly the transponder moves over the loop. But it is important to note that when the transponder is permanently activated, it will draw the battery empty within 1 week. So you only have 1 week of permanent activation. And this is important, because if you think about it, you may have cases where people are standing on the loop before they start. And if you add that up, this is actually the most critical part you can influence of how the transponders are discharged. If we look at failures in the field where people send transponders in where they are empty much sooner than the guaranteed battery life, it is typically a certain set of transponders, typically a tray of transponders, which was close to a loop for a longer period of time, permanently activated. So keep in mind, if the transponder is permanently activated, it only has 1 week of battery life. So now that we got the basics covered, let's talk about how you can actually read out the battery voltage and roughly estimate of what the status of the battery is. As you might know, with every single passing, the transponder does a measurement of its internal battery voltage and transmits it to the decoder. You have that information within Result 11 or your timing software, and it can be used to sort out transponders which are not good anymore. And let's look at what that voltage actually means. So the typical voltage curve looks a little bit like this, with the time or energy consumed in this direction and the volts in this direction. It normally starts off at 3 volts, and the cutoff voltage where the transponder stops working is at 1.8 volts. Now, you should not use the transponder down to 1.8 volts, because the way the measurement works, it is not representative of the moment where the battery is used the most by the transponder. So you need some headroom here, which we actually recommend is going down to 2.3 volts. If you see a voltage 2.3 or below, you should not use that transponder anymore. Now, the problematic thing about this diagram is that it is temperature dependent. So I'll draw a second curve, which basically looks like this. And this is for cold temperatures. So in the cold, the transponder will start off with a lower voltage, let's say about 2.7 volts. And it reaches 2.3 volts earlier, meaning that you cannot use an almost empty transponder in the cold. This is why we say there is a 50% line, which is somewhere here, and we only guarantee the whole temperature range of the transponder up to that 50%. Below the 50% line, we only guarantee minus 10 degrees Celsius. So when you have an event with minus 10 degrees Celsius or below, you need to make sure that your transponders are in the upper 50%. Now, the problem here is that when it's warm, the upper 50% is basically all within 3 volts. So you don't really see anything. So the rule here is that if you want to use a transponder in the cold, you need to cool it down to test it. We'll come to that in a later part of the video. Now, the 2.3 volts is the limit that we recommend for sorting out transponders. As you can see here, a transponder might still work in the warm when it's 2.3 volts, but will not work when it's cold anymore, because you are way below the 1.8 volts down here. So normally you start off with 3 volts and you end with 2.3 volts. And for the majority of the life of the transponders at normal room temperatures, you won't see big differences in the voltages. And at the end, there will be a very steep curve. And be assured that when you see 2.3 volts, the battery is almost empty. There is not a lot left. This is very steep at the end. Now, unfortunately, the measurement itself is not very precise. As you might imagine, when we designed the transponder, in the moment that the detection is recorded over your loop, we don't want to spend a lot of energy and time to precisely measure the battery voltage. So the battery voltage measurement is pretty imprecise. You can see variations up and down of 0.2 volts, just because of the way the measurement is done. So what is also recommended is that for a typical event where you have multiple passings, you look at the average that a transponder is reporting, not at one single data point, because of this variation that we have in the measurement. So what I would typically do is I would look for voltages 2.3 and below in your event file, in your data that you collected on an event. And if you see any with 2.3 or below, I would look at all the passings of that transponder and get an average and see if it's a transponder that needs to be sorted out. So what happens if the voltage drops below 1.8 volts? How can you detect that? So if that happens in your event because the battery is low or it's very cold, the transponder will reset itself. And when the transponder resets itself, there are three things happening. One thing is that the wake-up counter you can see in every single passing will reset to 2001. So whenever you see a wake-up counter of 2001, you know that that transponder has reset because of low battery. The next thing is that if you had tracking enabled, tracking stops. So that is important to know, because if you happen to use tracking and relying on tracking, it is important not to use transponders which are almost dead, because tracking just stops whenever the transponder resets because of low battery. Third thing, you lose any stored passing. So if there is any stored passing in the memory of the transponder, that will be lost on reset. So whenever you use tracking or you use stored passings, make absolutely sure that you are not on the edge looking at your battery voltages. So now that we got the voltages covered, one more question is, what does actually negatively influence the battery life of the transponder the most? And as I already said earlier, one of the major ways to discharge your transponder battery is to have it permanently activated. But actually there's more to it. On an event you can have it under control. You have a loop and you know that the transponder is in reach of that loop or not, because it wakes up and you see it, you see passings coming in. But the thing is that for the 5 years of battery that this transponder has, it has to monitor its surroundings for the 125 kilohertz loop frequency at any given time. I mean, you can pull this transponder over a loop within those 5 years at any given time, and it needs to wake up, it needs to detect the loop. So it is listening for 125 kilohertz all the time. Now, question is, how does that actually work and how does it influence the battery life? So what the transponder is doing is that it is in a sleep mode where it is just looking for any 125 kilohertz activity. So here it does not make any distinction between a loop or other 125 kilohertz signals, and they can come from other sources. Now, once the transponder sees a 125 kilohertz signal, it tries to see a wake-up pattern. Now, our wake-up pattern on the loop has a 16-bit length. So all 16 bits have to be received correctly before the transponder is really woken up. But for this to happen, the transponder needs to analyze the data on the 125 kilohertz, even if it's not coming from our loop. And this roughly doubles the energy consumption in standby. So it is important to make sure that the transponder, especially when stored away, does not see any 125 kilohertz fields. Now, to show you where 125 kilohertz fields can come from, we have in our lab this little detector device, which actually makes 125 kilohertz audible. And I will show you what happens. So if I take this here and I hold it close to a power supply, you can hear the 125 kilohertz. So it would not be clever to have the transponder close to this power supply for a longer period of time, because in a state like this, the transponder will be looking for the wake-up pattern continuously and discharging the battery at a much higher rate. Now, for the power supply, you can hear it, you can easily hear it. I will show you some other examples. So the camera that we're using to record this here actually emits a 125 kilohertz signal. The display that we are using in recording here emits a 125 kilohertz signal, and also the camera charger that we are using emits a 125 kilohertz signal. So you can easily understand that basically every electronic device, including your computer, generates a signal which leads the transponder into the wake-up pattern mode, which generates a higher power consumption. And this is especially important when storing the transponders away. So what do we recommend for storing the transponders? The storage of transponders should be in a cold room, because the other thing that affects the battery, self-discharging of the battery, is high temperatures. So store the transponders away from any electronics and electronic wiring in a cold room. That's the way you will have the most of it, and the transponders will last as long as possible. So one last thing, if you want to use these transponders for winter sports, how can you actually predict whether a transponder can still be used or not? Looking at the diagram again, the easiest way to actually do this is to cool it down. And we have two test scenarios that we recommend. One is using a normal fridge, not sub-freezing, just normal fridge, with about 5 degrees Celsius or 40 degrees Fahrenheit. And you will run into this part of the diagram, and you can see that a transponder is losing lots of voltage in that cold temperature compared to warm temperature, room temperatures. So if you have a transponder which gives you 2.3 or less at 5 degrees Celsius, 40 degrees Fahrenheit, you should not use it in the cold anymore. If you want to use it for an event with -10 or below, you should actually test it in a freezer. The problematic point about freezers is that their temperature can vary wildly. So if your freezer is really cold, it might be below the specified temperature of this transponder in general, then the transponder will not detect at all. So make sure that if you use a real freezer, that you know what the temperature actually is, so that you don't panic because all your transponders are not working anymore, because you're freezing them to a temperature where they don't work. So in normal cases, a normal fridge with 5 degrees Celsius, 40 degrees Fahrenheit is enough to give you this kind of picture. And if you see 2.3 volts or below at 5 degrees, you shouldn't use it in the cold anymore. Only if you have very cold events, do the freezing test. Feel free to contact us in support if you need more help on this. It is actually not easy to forecast the real world, very low temperature performance of a transponder once it has gotten above 50% of its lifetime. So, I hope this video was helpful. It is obviously a very long and technical video again, but we had many questions about transponders coming to the end of the life. Typically, the first transponders that we shipped out 6 or 7 years ago are coming to their natural end at the moment and need replacement. This is why this topic is important now. And just keep in mind, these batteries have a limited lifetime. They have no endless capacity. So you have to expect to replace them at some time, and you should be prepared for that. And you should know how to actually look at the data so that you sort them out at the right point in time. So thanks for watching and hope to see you next time.